Hello everybody. Let us wait for a few minutes. Then I will start. Uh, give Let us give 2 to 3 minutes such that other people can join. Then I will start. Okay, let us start. It is already 5 minutes past after 5 o'clock. In between the lecture, I think many other people will join, and I will add them. But yes, so finally we have completed 50% of this course, and other 50% is left. So let me briefly today first introduce once go through the topics that we have already learned, and that we have already learned and what are the topics that we are going to discuss today. And I hope every one of you are enjoying this course, and this is the week 5 tutorial. Welcome back again to all of you. And today we will discuss about some new topics, some revision, some questions, and I promised you guys that I will definitely do the modeling of a star topic, because that was told once in the lecture, in one of the lecture. I forgot which lecture, but that time it was not discussed at all. And I was just finding out a good timing in this course, such that where I can start the modeling of a star, and I think it is a perfect timing to know about that. But before that, we will obviously solve the questions usually what we do in every classes. And But before that, I will definitely give a recap or revision of whatever we have learned in the 50% of the course, because we have already reached to okay, somebody, Godhuli is asking for the book. Okay, I think, okay, I'll share. Actually, officially, we are not allowed to share any online version of a book. That's why I am not sharing. But if you guys tell, then I'll try talk to them and I'll try to share that, because that is not a very official thing. That's why. Okay, but I'll try. And yes, okay. So let's start our discussion today. Uh, and I'll show some of the things to you today. So, some, I'll talk about some of the websites, like where you can get some. That is website maintained by some university or institute, from where you can get many data, many things that you can directly learn. Like we talk about the half life. This has this half life. This has this. From where we get the data, that I will show you today, that from where you, without taking any help of book or anything else, even when some professor design any problem or questions, they also take help of that library that you can call as a open source library or anything. So that is a website that I will talk about. I will show that how you can find out the stable nuclear the nucleus stable, which one is stable, which one is unstable, and the half life, and any data, what is if it is doing beta decay or what it is decaying to, all those things I will show you. And you will find it very interesting, because they because there all the data are given. And I'm sorry for the noisy background. But yes, let's just start today's discussion by discussing about what we have learned in the 50% of this book. But yes, as I usually mention every time, let me mention those things again, that obviously, if you are finding any problem anytime, oh god, then please write the questions to ask a question portal, or you can directly mail me, or you can ask here by unmuting yourself, or by writing in the chat box, or you can use the YouTube chat box also. And yes, obviously we have a YouTube link also for where I upload these videos, where you can find out the lectures later on. If you find out, if you find any difficulty to understand and find that you have to revisit those things again, then you can check out the YouTube link. And and if anybody misses any class, then please do visit that and check that. All right. So what we have learned till now is that first we have introduced uh, to the nuclear astrophysics course, that what was there in the what is nuclear astrophysics, what we are going to learn here. And by now I think everybody has the vibes that what we are learning here, and why we what we can what we can think, that what we will be ending up with, what we will learn till the end of this course. And what is nuclear astrophysics. Suppose if anybody is asking you that what is nuclear astrophysics, because many has asked me sometimes, some point of time, that what is nuclear astrophysics, because people have heard about astrophysics and nuclear physics, but not nuclear astrophysics. So this is an area. So now you know about these things. So we have introduced and gave a proper background to this subject. And now then we move to the main topics, where first main topic was elemental abundance card. First main topic was elemental abundance card, which was very important to us, which is very important in this course. Then evidence of nucleosynthesis. The three evidences were elaboratively talked about, were in three lectures, I think. And there are lots of discussion about this, and you know that what are those evidences of nucleosynthesis and what is nucleosynthesis. Then in the discussion session, we have also discussed about We have also discussed about cosmic microwave background, Hubble's constant. Then we went to the luminosity, and one of the most important thing, that is HR diagram. Then we talked about reaction cross section and many thing in between. They have come up, but I am not writing those things. I have written only those things which are very important in this course and which you have already learned, and with very elaborative manner. So I think you guys are pretty happy that you know all these topics by now, and I hope you everybody has pretty good understanding in these topics by this time. So next we have gone through the reaction cross section, reaction rate. Then I also talked about plasma, thermal energy, why Maxwell Boltzmann statistics is used, all those things. Then one of the main thing here was also the cross section and cross section reaction rate, because here, as it is nuclear astrophysics, which reactions are taking place and what is the cross section rate, that is very important here. And you have learned many topics of nuclear physics as well. We have also gone through life cycle of stars, then apparent and absolute magnitude, astronomical distances, liquid drop model, shell model, reactions, quantum tunneling, photo disintegration, astrophysical S factor, all those things. And one of the important thing here is also the cell model, and I have discussed a lot of things about the cell model, and I hope everybody is clear about it by now. But I also again told you that if anybody has any problem with the cell model, then please let me know, and because you need to learn that, and you need to get you need to be like that much able that you can find out the ground state of any nuclei. We also talked about liquid drop model and what is the drawback, why you went to the cell model, and all those. And reaction rate, that was there was a whole lot of discussion about these things in the lecture series. That's why I have not gone through the reactions very elaborative manner. Rather, which topics are not well elaborated in the lectures, I gone through those topics more rigorously. Then somebody asked a question about quantum tunneling, and in the previous class, I discussed about quantum tunneling, photo disintegration also, and S factor also. If anybody has missed any of the topic, then please visit to the to the YouTube channel and check that again. And if anybody needs any help, then please, you are welcome. Okay, so previous day it was lots of discussion, and the it was I at last moment it was I was a bit doing a bit hurry up because of lots of time was already passed, and I left with one problem which was not covered that time. So I'll start with that problem, and that will be kind of revision to the course also, revision to the previous lectures also. And then I'll go to the recap of week 5 topics. And if anybody has any problem in cell model, let me know in between by writing by writing to the in the chat box. And then I'll go to the recap of week 5, and then let's solve some new questions of this as week 5, and I'll end up by introducing the modeling of a star. And in between, obviously, I'll go to the that website which I was talking about. So today I have a lot of things to show you and a lot of things to discuss, and please feel free to discuss with me and discuss with anybody in your class. If you have any email ID and all those things, discuss in the ask a question portal. That will definitely help. Okay, so what you have learned in the week 5, you have learned about the neutron induced non-resonant reactions, then the burning stages of stars and hydrogen burning. You have learned about PP chain and CN cycle, CN or CNO cycle, then cell model, gamma decay. And PP chain and CNO cycle are very important that you should know. So I will, and this time again the reaction part is pretty much very good, very well covered in the lectures. That's why I am not talking much about the reactions, because that is literally very good. That is already elaborated in very good manner in the lectures. But yes, I will definitely solve the question and discuss a few things and the main key formulas, what you need to what you need to remember. And previous day also I gave you I made some sort of like formula sheet, that which formula you need to remember. Those formulas, obviously I hope that everybody will try to revisit those things and remember those things. That's what we need, what the formulas are needed to solve those kind of questions. And previous class was mostly I discussed a lot of things, but the later half was a lots of questions, mathematical or numerical questions, which you can expect in your end term examination. So if anybody is, and those are most of your assignment 4 questions, and I solved those intentionally, because you need to know the each and every step of those numerical problems, otherwise you will not be able to solve those. So I request again to everyone that please try to solve those questions by yourself. Again, you have all the material in the shared drive, Google Drive folder. If anybody is not there, then please send an access request. I'll definitely add you and give you the access request, access, such that you can see those materials. I usually upload all the solutions and all the question answers, and also some new materials, and the discussion sessions whatever is there, and also the slides. So everything is there. And I like to mention one thing, that I have shared to one more extra material there. You can check whoever is there, and if somebody is not there, then please if somebody is not joined there, then please send an access request. I'll give the access and you can see the materials there. That will be literally helpful for you. Okay. So what we will do today? Today, as I said, I'll first the revision part, that what you have learned, that I have already talked about, and the last question that I have missed yesterday, previous day, that I'll start with that. Then then some miscellaneous problem we'll do, and then some few important points of week 5 I'll give. Then I'll go to the website that is called NNDC, and then modeling of a star. So first start with this question 10 of week 4, which I have left with. That question 10 was that temperature dependence of let me write this question also, because here I have not written in the latex, so the notations are pretty bad. So question 10 of week 4. If anybody can solve or has already solved, then please I will ask after the writing the question, that how you have solved, and how what you have done, and what is the answer. Excuse me. All right, so let me write the question. The question is the temperature dependence of any sigma v near some energy t equal to t0 can be given by introducing a power law, which is like n a sigma v n a sigma v t0 t by t0 n. Now the question is the value of n for the alpha plus 12C reaction at T equal to 200 megakelvin is what? There is not given any uh, any options here, but I can give you some option also if you need, like A 0.6, B 7.6, C 17.6, D 27.6, E 37.6. So these are the five options. Now anybody, if anybody can do the, I'll give you 2 minutes, or if anybody has already done this, then please let me know, because I have already shown this problem in previous class also, but I told you guys that I will once again go through these, as the last time it was, I just left it almost, I just ended up very by doing very hurried up manner. So I will not. I'll discuss it again today. So that's why I am asking, if anybody has done already, then please share that what you have done. And I have also, also showed this. But if anybody has any doubt about this, then also let me know. But yes, but I would like to see that if you that you guys have tried. I'll give 2 minutes if anybody wants to tell anything, or if anybody wants to discuss anything, or tell that how to solve. Then it's very nice. Otherwise, I'll solve after 2 minutes. And these were the formulas that I written in previous classes, which are the main formulas to use for this type of for solving this type of questions. Today I'll give a short revision of this again, but in between that, please, you guys, please try the question by yourself, that how to solve this. Okay, so let me wait for 2 minutes, and in between that, whoever is trying, please try. I will go through the main formulas that you need to remember. First formula was that I was given. I was discussed about the effective burning energy formula, that you need to remember is zero is equal to 1.22 Z1 square Z2 square mu Tc square whole to the power one third. That is in kilo electron volt. And here, one thing to remember, that you need to know and be cautious about the units, because most of the problems arise by doing mistake in calculating the units, because units are a bit different here. So I am several times telling you, and I'll again tell you, that please make sure that you are with right unit. And I have shown you the also one in second week lecture, I think, that took the conversion of the units. That is very important, that's why I gave some time on that. But yes, please remember that. And I hope by now everybody is aware about how to calculate this mu, because in previous class, somebody became confused, and it is very natural to be confused. I also used to be once when I did these type of courses. But yes, I think by now everybody is aware about how to calculate mu. The next thing, I talked about the Coulomb barrier, that is the formula 2, which is simply Z1 Z2 is squared by R. The third thing, I talked about the width of Gamow peak. The formula is like this: delta is equal to 0.749 Z1 square Z2 square mu T6 to the power 5 whole to the power 16. Now the Imax, how it varies with the tau, what is the tau constant, how and this formula is formula number 4. And I hope that everybody every if but yes, let me tell you one thing, that what I also used to do during my examinations, that making a formula sheet, though that is not a very good idea in terms of understanding something, because you need to understand it. But in terms of examination purpose, you need to make some formula sheet, that always helps. Okay, so you can also make it. So that is the formula 4. And now the formula 5, it is reaction cross section, that is sigma E equal to 1 by E to the power minus 2 pi eta AC, and e to the power minus 2 pi eta, we know that we know this is another constant, and AC is the Sommerfeld S factor. It 2 pi eta, I will come to that factor again today. And this was the formula 5 and 6. What is 2 pi eta, how it varies with mu and energy, and most of the things are varying with the energy. Keep that in eye, that what are the variables. because that is important to understand when you will do the modeling of a star. That's why I was trying to find out a perfect timing where when we can start to talk about the modeling of a star. Okay, so that was that was the formula 6. Now the formula 7 is sigma v, average of it, that is the rate. And it is a very common question to find out the rate, and you need to know and remember that how it is varying with the energy, with AC, with several things, because this rate has several different structure of formula. Those are same, but for different cases we use those things. Now the after that, yes, this is another that is directly for varying with the tau that I mentioned, that was the formula 8, and this is a formula 9. These formula 8 and 9 are related with the question that I have given you right now. So I solved the question. So these are the main formulas, and by this time I have already I am already over with more than 2 minutes. So anybody has tried this question in this time, and please, if anybody has tried, then please let me know what is the answer. The question was, the temperature dependence of Na sigma v near some energy t equal to T0 can be given by introducing a power law. This the value of N for the alpha plus 12C reaction at T equal to 200 mega Kelvin is what? So please answer it. Okay, somebody is asking for the access. I'll give her the access. In between, please let me know if anybody has solved.
Ma'am, 17.6, ma'am.
Okay, yeah, I'll tell the answer. And if anybody else. Okay, Godhuli, I have given the access to you. You can see, you can get the access of the folder now. Okay, all right. Naresh Nandu has answered it that it is 17.6, and I think he or she was telling about this answer right now by unmuting him or herself. But yes, she is absolutely correct that it is 17.6. Can you please explain that how you have solved this to your friends?
Yes, ma'am.
Yes.
We have to solve by using the formula tau formula, ma'am.
Hmm. Yes.
So the tau equal to 42.46
Yes.
Z1 square Z2 square mu by T6 whole power 1 by 3. Then in the case of reaction, right, that alpha plus 12C.
Yes. Yes.
In
Yes.
order to calculate that, we have to use the formula mu, that mu formula Z1, Z2, then all do that temperature T6 is 200, right, ma'am? So we
Yes.
have to use this formula and solve the final answer, ma'am.
Absolutely, absolutely correct. Whatever he or she has told, that is absolutely correct. But yes, now let me solve this problem. Then you will get the idea that how to solve. And whoever is solved, very nice, very nice. So let me solve that question now. The first thing is that, as he or she has mentioned, that okay, this is color. So first thing is that the tau is equal to 42.46 Z1 square Z2 square mu by T6 whole to the power 1/3. For what was the reaction? Reaction was alpha plus 12C. Z1 is equal to 2, Z2 is equal to 6 in this reaction. That I think everybody has understand this up to this part. Now we have to calculate mu. We know Z1, we know Z2. Now we need to know about mu. We also know about T6, that is equal to 200 megakelvin. Now mu is equal to m1 m2 by m1 plus m2. That will be 4 into 12 by 4 plus 12 equal to 3. Now I'll calculate the tau, that is 42.46, 2 square, 6 square, 3, 200, 1/3. Remember, this is already given in mega Kelvin, that's why I am directly writing the 200. Very you need
Ma'am,
to be, yes.
ma'am, if the formula is T6 and we are given the value of temperature in gigakelvin, then how to convert?
If you have gigakelvin, 200, suppose gigakelvin means 200 into 10 to the power 9 Kelvin. Okay, so that means 200 into 10 to the power 6 into 10 to the power 3 Kelvin. That means 200 into 10 to the power 3 mega Kelvin. You need to put this 200 into 10 to the power 3 then in this denominator.
Okay, ma'am.
All right, so this is the thing that, and then you need to calculate, then if you calculate this, then you will get 54.9, that is the value of tau. Now what is the relation between tau n and tau? That is n equal to tau minus 2 by 3, that I have shown to you in the previous day's discussion, that how it is varying with tau minus 2 by 3. It was coming in by comparing the power of the both side. So and if you now calculate this, then you will get like 54.9 minus 2 by 3, that is equal to nearly 17.6. So this is the n value that you need to calculate here, that was given in the question. So now you have solved that what is n, and this is the way how you will solve this type of question. And this type of questions are very important for your end-term question. And there was also another question that I discussed in previous day itself, that in the question 9, that was also a similar question. And now I think everybody can understand this type of question and solve this type of question. And yes, week 4 assignment was very important for you guys. Please do those problems by yourself again, by seeing the materials and discussion sessions, and then try it by yourself. So okay, so this was the last thing that I could not cover previous day, so I have done that. Now I'll go with this today's materials. Today's material is that, um, but yes, before that I want to ask you one thing, that is everybody clear about cell model? I have discussed that in week 3, and I have also discussed it in week 4 because of some questions that you were not able to solve. So now I am again asking the question that if you have understood the cell model nicely or not. Manisha has written that she has understood. That's great. And anybody else? I
Yes,
think
ma'am.
previous time
Understood,
also.
ma'am.
Okay. Previous time also Manisha gave and Naresh gave the answers and they were correct. So yes, anybody else has any problem, then please let me know. Don't be shy, and yes. Otherwise, I'll move with the next topics and I will not discuss the cell model again then. Okay. So I hope everybody is clear with that, and then let me go to this, that what are the main topics that you have learned in week 5, because there were some key points here in this in this week's content. First was that by now everybody know about how to write the reaction, but by not writing the whole reaction, that means the short form of the reaction, that everybody has learned by now, I hope. And the general neutron induced reaction, that was the this time the for this week 5 content, the main thing was neutron induced reaction. And what is a general neutron induced reaction? That is, that can be written like x n a y, where a can be gamma for radiative capture, or otherwise it can be alpha particle or proton. Okay, so this is the general neutron induced reaction. And you have also learned about neutron wave, and I hope this is a pretty wide concept to you. Obviously, those who are aware about the quantum mechanical behavior, and we consider that particle and wave nature, the dual nature of matter simultaneously, those are not, they are not very they have not feel that awareness very much. But those who are not aware about the quantum mechanical behavior, they must be very much curious and very like how this can be possible. But yes, as we know that if, we know that we consider the existence of wave particle duality of matter, and that's why we talk about neutron wave. And why you are not talking about proton wave and electron wave and other things? Because neutron wave is important, because because it can penetrate some of the solids and liquids which charged particle, that is proton and electron, that cannot. That's why neutron wave is important to know, but not the other so much. So neutron wave is indifferent to the charge of a nucleus or electrons. Neutrons can penetrate the solids or some solids and liquids where the charged particles cannot penetrate. That is the main important key concept about the neutron wave. So why we are that's why we are discussing about neutron wave. So neutron wave can be of two kind, P wave and S wave. And P wave and S wave, you all have idea about these things, because this is a plus 2 level concept. But maybe you have not learned in terms of P waves or S waves. Rather, you have learned about, in terms of transverse waves and longitudinal waves. This P wave, S wave terms mainly used in case of seismology. That means when some earthquake comes, then the what generates in the epicenter of it, that is primary wave, and the propagation of it, which is called the secondary wave, that is a transverse wave. Now that so transverse wave, so that is, it is like a very different kind of thing, like it is generating like a longitudinal wave, but when it is propagating or or becoming the secondary wave, then it is propagating as a transverse wave. So this is a peculiar behavior, but these are the two nature of waves which can be simultaneously seen. Now now let me go to this short gifs, that it is showing about the S wave and P wave. The S wave is nothing but the transverse wave, that how it is propagating. Like when it propagates through a medium, it shakes the medium in the direction perpendicular to which it is moving. And P wave is that wave which is a pressure wave, like longitudinal. So it shakes the medium in the direction in which in the direction in which it is propagating. That means it is in parallel with the medium. It is shaking the medium in parallel with whatever is it is propagating. So these are the two main differences of S wave and P wave. And but you will be surprised by one information, that if you think that which wave is much more which has much more energy, such that it has much more power to shake the medium, then it is S wave. The transverse wave has a much more energy or power to shake the medium, not the P wave. Okay, so now you know about the neutron wave. This is a summary of the P wave and S wave, and I wanted to show you the visualization. I want to give you the visualization of S wave and P wave. But now let me write a few words about this, such that you can use this as a note and remember it in later half also, after completing of this course also. Like it is saying that mm, in different to the charge of a nucleus or its electrons, neutrons can penetrate where charged particles cannot. So this is the main thing of neutron wave. And why it is neutron wave? Because of wave particle duality. And this can be of two types: P wave, which you can tell as the short form of pressure wave, and another is S wave, which you can think of short form of shear wave. Okay, so this is compression wave, this is obviously shear wave. This can move through solid and liquid. It can only move through solids only. Shake the medium in the direction in which they are propagating. And it is like shaking the medium perpendicular to which it is moving. So this is a P wave and S wave, and what is the difference between them? So now I'd like to talk about the energy dependence of sigma, because we are talking a lot about we are talking a lot about sorry, let me just show these things once, like what I have written. I think these are visible. So yeah, for the video making purpose, let me go through this once again, because I was in different tab. The neutron wave is the wave particle, a neutron wave we are talking about, because this is as part of wave particle duality, because of its wave particle duality, because we know which we know from the quantum mechanical perspective. And but it is different to the charge of a nucleus or its electrons, because neutrons can penetrate when where charged particle cannot. And there are two kind of modes, like P wave mode or S wave mode. One is pressure wave and another is shear wave. So pressure wave is compression wave, S wave is shear wave, that is the like transverse wave. Let me write here that this is like transverse wave. Then P wave is moved through solid and liquid, S wave through solid only. Its P wave shake the medium in the direction in which they are propagating, and S wave shaking medium perpendicular to their which they are moving. Now the next thing is energy dependence of sigma. We are talking about the cross section several times, and we are writing in every time that sigma is a function of energy. And we are finding the sigma v, that is the reaction rate, that is also a function of energy, as sigma is also a function of energy. But yes, but we need to check that how it is varying. We need to know that how it will vary for this reaction, for this neutron reactions. And this formula has been derived in the lectures. so I'll not derive, I'll just give the formula which you need to remember. Energy dependence of sigma, so rate becomes sigma v 8 by pi mu whole to the power half 1 by kt whole to the power 3 by 2 integration is 0 to infinity e sigma e to the power minus e by kt d, which can be equivalently written as 0 to infinity e l plus half l, you know the angular momentum number, e to the power minus e by kt d. I hope everybody has gone through the lectures of week 5, then they can easily catch up the things which I am writing at this moment. So sigma l is 1 by v square tau l, and which is equivalent to e to the power l plus half v square. If we substitute that, then what we are getting is this. Let me box it again because you need to remember this. Okay, now after that, what you have done in the lectures, you have calculated the age of sun, which becomes 4.5 into 10 to the power 9 years at present. Then you have learned about PP chain and CNO cycle. But let me go through this once. So this is the PP chain. What are the PP chain and what is the PP chain and what is the CNO cycle? PP chain is a nuclear fusion reaction by which stars convert hydrogen to helium. In CNO cycle also, by nuclear fusion reaction, stars convert hydrogen to helium. But CNO cycle mostly happens for massive stars, at least which are greater than 1.3 solar mass. That's why most of the time, in case of our sun, obviously PP chain and CNO cycle both are happening because there are heavier element in our sun also at this moment. But the main thing which is dominating for our sun at this moment, that is PP chain, and PP chain is converting hydrogen to helium inside the star. And this is the reaction, like we have H, one H, that is a hydrogen, and when they are doing the nuclear fusion due to very high temperature, then it is producing mu, and it is some of the other particles, and it is becoming to 2H2 and again 1H, then it is producing gamma 3He, and ultimately by doing all this reaction it is producing 4He, that is the helium. So this is the reaction. If you can remember or you cannot even, because these reactions are given and it will not be asked in your question or in term examination, I hope. But this is a good thing to know that how a PP chain works, and why it is called PP chain, because this is an hydrogen, this is an hydrogen, and mainly they have one proton, nothing else. So these are coming together, and due to the nuclear fusion for higher temperature it is producing 4He. That means to lower Z value, it is going to the upper Z value, and we know that for nuclear fusion we need much more temperature than the nuclear fusion. And I hope everybody has clear idea of nuclear fusion in nuclear fission by now. And this is the CNO cycle. This is much more complicated cycle, and here also it is converting to hydrogen and helium, and in between from the heavier element, like it has nitrogen, it has carbon, it has oxygen and all those things, and some amount of gamma is producing, hydrogen is coming, helium is producing, all those things are happening here. And this is the cycle that happened for the CNO. And you have already known about those facts also. This is that PP chain has not only the one single probability of a reaction, but it has four probability, like PP chain 1, 2, 3, 4. There are many kind of many other many kind of PP reaction chain that is happening there. And for the CNO cycle also, there are CNO cycle type 1, type 2, type 3, type 4. So those are also discussed in the lectures, but I just showed you just to remember this thing, or just to give the reaction with the visualization, and you can find it in internet also, because I have taken it from the internet also, and I found these things very pretty well elaborated pictures that can visualize that what is happening in case of pp chain and CNO cycle. Okay, so this is the this is the, and this was the revision of week 5. Now I'll go to the uh, problem solving session of for week 5. But before that, I would like to introduce one more thing, that is the interaction and matter, because we are talking about neutron. In the lectures, it was also talked about neutrino or neutrino, whatever you can pronounce it. And then we are talking about sometime electron. Maybe we'll next somehow sometime we'll talk about tau, or maybe you have already heard about those things. But you need to have a clear vision of that, what are the difference and what are these. Like these like matter are basically made up of three things, like quarks, leptons and bosons, and they have several categories in which the some neutron, electron, they fall. Some of them are quarks, some of them are bosons. Bosons are nothing but the mediators for which we can see the interaction between matter. There are only four kind of interaction or force exist in nature, that we all know. And these things, I think, is never told in the lectures. That's why I want to mention it once, such that you have a very clear idea of these particles, metals, and interactions. So let me write it here, like in this manner. Okay, uh, maybe interaction. No, then you will be not be able to see. Okay, let me write it that also. We only like first is interaction. We know there are four. We know there are four interaction. Then the relative strength, then the range of that. I'll not talk about the characteristic time, which is another important thing, but let's not go into that. But mediators, that is important, because I want to talk about the basic fundamental particles with which the matters actually made up of. And these are the fundamental particles that was consecutively generated after the Big Bang. So the first interaction, first is, which is the most strong interaction, is a strong force or strong interaction. And we will talk other interaction in terms of the strong interaction. So the relative strength of the strong interaction, let us consider 1, that is the highest. Then with respect to the strong force, what is the interaction strength of other force, that we will discuss. This is the reference point, like strong force is a reference, and with respect to that reference, we will talk about the how much is the strength of the other forces. So the strong force, then we know about the electromagnetic interaction or electromagnetic force. And then we know about the weak force or weak interaction, and last but not the least, gravitational interaction. And strength will decrease in this manner. That means the strongest interaction is possible in case of strong force. Then it is EM force. Then it is weak force, not the gravitational. It is weak force, and last but not the least, it is gravitation. Then with respect to these strong force, the strength of the electromagnetic force is 10 to the power minus 3 about. The strength of the relative strength of the weak force is 10 to the power minus 13, and gravitational is 10 to the power minus 40. That means you can understand less how much less attractive this force is. I should not use the attractive word, because we know that this attraction is not any attraction or repulsion, rather it is the curvature of space time upon which these things that happens in gravitational interaction. But okay, so this is but we can say that the relative strength of this force is the least and highest is strong force. Then the range is important because up to which range we can feel these interaction. That is very important to know, because then we can visualize that where the strong force works, where this electromagnetic force works, where weak and gravitational force work. So this has the 10 to the power minus 15 meter range. Now you have the idea that what is the 10 to the power minus 15 meter range. Within this is the range under which a nucleus can only form. Like nucleus has a radius like r0 to the power one third, then r0 is of some femtometer order, and this is femtometer order. So you can visualize now, or you can think it of now, that it has range of 10 to the minus 15 meter. That means the strong force can only work inside a nucleus. Then the electromagnetic force, which is long range. Weak force is also 10 to the minus 18. That means it also works in very narrow within the nucleus only. Other than that, it does not work. And gravitational is also a long range force. Then the what are the mediators? Mediators are those particles which is the interactor particle due to which this interaction is happening. Like if you say two there is a very famous example, like two persons are standing over there, person 1 and person 2, and they are throwing a ball, and he or she again throwing a ball. Okay, so this like they are interacting now. There was no interaction, now they are interacting via the ball. He will send the ball, again she will send the ball. By this way they are interacting, and this ball is the thing which is actually making it possible that they are interacting, and this ball is which is called mediator. You can compare that ball with the concept of mediator. Like when any force work, like if I consider this is my hand, and I have kept this pencil here, then it is stand over there. It is not. It is just over my hand. Why it is over my hand? Because there is some electromagnetic force is reacting over there, and for that they are passing through some mediators. They are sending some mediators. And what is the mediator for the electromagnetic force? That is nothing but the photons. We cannot see the interaction of the photon because that is very negligible, and that is not in the order of such wavelengths such that we can see, but it is in some other some other spectrum of electromagnetic spectrum, whole spectrum. So if it is like this, then there is working the electromagnetic force, and their mediator is photon. For strong force also they have some mediators, and for this it calls gluons. Then for weak it is W plus, W minus and Z0. And for gravitation called it graviton. But the thing is that it is not discovered yet, and we know that we everyone everyone of us are aware about that graviton is not discovered yet. But people think this way, that maybe there will be some existence of graviton, and there are lots of discussion, lots of it will happen or not happen, those kind of phenomena are there. But yes, these are the four interaction, these are the relative strength of them, and this is the range, and these are the mediators which are working to support these reactions. Okay, now method. Any method is made up of 1 minute. Sorry, I sorry, somehow I lost my internet by knowing this, by not knowing about this.
Ma'am, past through 2 or 3 minutes were not audible to
Okay,
us.
somehow I lost my network and I couldn't realize it. So I was talking and now I realize. All right. So uh, now you can hear and see the things.
Yes, ma'am.
All right.
Yes, ma'am.
Okay. Okay. So I was talking about the interaction and what are the I was talking about the interaction and now I was just about to start to talk about matter. Any matter, any matter is made up of particles, and they are fundamental particles. There are some fundamental particles upon which the other heavier particles are generated, and the fundamental particles which are there in our universe, those can be subdivided or divided in three categories. One is quark, second is leptons, and third is bosons. And the mediators which I was talking about, these are nothing but the bosons. Now the quarks are, there are total 12 quarks, and among these 12 quarks they are called as up, the up, wait, then down, charm, top, charm and strange, top and bottom. So these are now six, but they have antiparticle. Every particle has some antiparticle, and considering this particle and antiparticle, there are total 12 quarks. These are written in terms of bar. U bar, C bar, T bar. Those are the antiparticles of up, charm, top, and down, strange, bottom. These has the 2 by 3 electronic charge, and these has the 1 by 3 electronic charge. So these are the 12 fundamental quark particles which are there. Then there come the leptons. Leptons are again 12, and they are first is that electron, muon, and tau. These are the particle now, then with the negative sign, and they have the antiparticle electron positive, that is called positron, then the positive muon and positive tau. Again we have neutrino. So neutrino falls into the category of leptons. So neutrino comes as electron neutrino, muon neutrino, tau neutrino, and positron neutrino, mu plus positive muon neutrino, positive tau neutrino. So these are all leptons. These have plus charges, these have minus charge. Not plus charges, like in any reaction, if a negative particle, that is the particle, and these are also the particles, and these are their antiparticles, then present of particles is plus 1 and present of antiparticles is minus 1. So these are called the leptons. And last but not the least, we have bosons, which are the cause of any interaction, and we have 7 bosons: gluon, photon, W plus, W minus, Z0, graviton. Now you will say that there are only 6. what is the seventh one? The seventh one is you all are aware of, which was a great discovery in 2012, I guess, the Higgs boson. So these are the fundamental particles that exist in nature, and these are the fundamental particles with which the matter is made up. First thing is quark, then lepton, then boson. Boson is the cause of the any interaction, and there are four fundamental interaction: strong, electromagnetic, weak, gravitation. Now there comes hadrons. Now you say that what is hadron? Hadrons means heavier particle, which made up of these fundamental particles, and they are mostly of two kinds. One is mesons, you know about these things I think, and another is baryons. If I am making any mistake in spelling, then please consider it, because I don't know, I don't care about the spelling sometimes. Okay, so mesons are made up of one quark and one antiquark, and baryons are made up of combination of three quarks and antiquarks. Maybe quark, antiquark, antiquark, quark, antiquark, anything can be possible, but combination of three quarks. Quarks means quarks or antiquarks, anything. So there are many baryons. There are baryon decuplate, meson octuplate, baryon octuplate. All these things are there, but you don't need to know about these things at this moment. So these are the fundamental particles that I wanted to talk about, and yes. So now I am almost in the position of solving today's problem set, and okay, I don't have any further topic to discuss about newly, but yes, now I will solve the questions, but before that I'll just go through that what we have done till now. First, I shown you that what we have learned till now, and you can realize that in the 50% of your journey you have already known about many things. Now I have solved the problem 10, and I hope you are all clear that how to solve these kind of numerical problems now. Then the highlights, these are very important to remember that what was the main key concepts of this week 5 lectures. Then I went to the interaction, and what are the main four interactions, and what are the mediators, what are the fundamental particles, how matter, what with which the matter is made up of, and what like what are the categories of that, and what are the total number of particles, and you know that which are what are the things at this moment. So you have the idea of the particles also. So now I'll directly go to the problem solving session, like what are the problem that I want to discuss today. Some of them again is from your assignment, because we have been told that assignment need to be solved in the discussion session, because whatever you are getting in your assignment, that is very important to know that how to solve them. That will only help you in your in semester in term examination. So now let me present that slide again. So these are the question. This is the question 1, 2, but I need to share the writing pad also, such that I can write it simultaneously here. Okay. Okay, so first question is, question 1 is, it is telling what is the minimum temperature required for the fusion of two protons classically. I am not writing the question again here because it is already shown in the slide that the question is telling what is the minimum temperature, that is a T min, you need to calculate for the fusion of two protons classically. Classically means you don't need to think about any quantum mechanical or anything like that. You just can use the classical kinetic and energy theory or Maxwell Boltzmann energy distribution kind of thing. You don't need even need to go there, but yes, you can think it classically, that what you need to do. So we just need to calculate the T, and we know that energy is equal to kBT, nothing else. So T mean, as it is mentioned, it is classical. So T mean is equal to E by KB, that is equal to and we know that
Ma'am,
in a yes,
ma'am, the most probable energy formula is half kBT.
yes, uh, you can even if you do not half kBT, then it will not match with the options given there, but you can use half kBT also. But in this whole analysis of this nuclear astrophysics course, you have always calculated kBT, never half kBT, because in plasma physics and in case of doing any astronomical analysis of these kind of things, the half factor does not matter, and we write everything in terms of kBT actually. That's why we are calculating kBT every time.
Okay, ma'am.
Okay, so the T mean is E by kb, and for the PP reaction, it was told in your lecture and discussed many times by now, the energy produced is 550 keV, that is equal to 550 into 10 to the power 3 ev. So we'll some information you need to remember, like what Godhuli just mentioned, that why it is kBT not half kBT. So we are using kBT for previous questions also and for now also. Again, the PP reaction, like what is the energy that is what is the amount of energy that happen in when the PP reaction happens. So that is, you also need to remember this kind of information. You can write in a page and remember it, that what are the information that which we are using very often in this course. Okay, it will help you. Then it is 550 into 10 to the power 3 by kb is 8.62 into 10 to the power minus 5. This is ev and this is ev per Kelvin. So ultimately, if you calculate, then it will be 6.3 and 9 Kelvin. So this is a question 1, and this is a very easy. This was a very easy question, so I don't need to
Ma'am,
discuss. Yes.
ma'am, if the first question is proton plus deuteron, then what will be the answer?
Then you need to know
What will be
about
the
the energy
process?
produced in proton deuteron reaction, and
Actually,
if
in the previous assignment, this question was given.
Mhm.
That means the classically what will be the minimum temperature proton for proton and deuteron?
Okay, so for proton deuteron, the information about the energy was given to you or not?
No, it was not given the energy. The energy was not given.
Was not given. Then if it was not given, then you need to calculate it just by like the binding energy calculation.
Okay.
And
But the answer is same because already the last date over out. That's why we know the answer.
okay,
Okay, 6.4 into 10 to the power 9 Kelvin.
okay.
That means in proton and deuteron case, the energy is same because the
Proton is
temperature.
what is proton? In proton, that means you can consider it as 1 H, and deuteron is 2 H. Like there are okay. So the thing is, I don't know about the question, what you were talking about, but what I can tell that maybe they have the same. amount of an okay, actually because of the gamma peak, maybe this reaction has the same gamma peak.
Okay.
All right, so that's why but yes, at this moment I can't tell you an quantitative answer like yes, this for the gamma peak this is this, that's why it is like this. But maybe that is a possible reason, that's why they are saying.
Okay, ma'am.
All right. So the okay, maybe I'll check again. But yes, if it is like that, then it can be a possible thing. But yes, but because the gamma thing is very important when you are doing any reactions and calculating this stuff. All right. So the next question is which nuclear reaction is responsible for a very long lifetime of sun? And I have not given any option here because this was your assignment question. I guess I forgot, but it was in the lecture also. But do anybody can tell about this, that which was the reaction, or maybe write in the chat box, or maybe I can give the options. Let me write the options. Then you can tell. Tell me which one is the right answer. That which nuclear reaction is responsible for very long lifetime of the sun?
Number D.
Number D. Monisha is also telling number D. Pintu is telling number D. Godhuli is telling number D. And other persons, please. You can tell like if it is wrong or right. That does not matter. But participation is matter. Nanda Kumar is telling D. Other. Okay, all right. And this answer is obviously right. You guys, every one of you are right. That the answer is D. Now the question 3. Question 3 is how much of hydrogen in the sun is involved in the hydrogen burning process? This is also informative question, and in between some lecture it was told. The options are given to you: 0.1%, 1.0%, 10%, 100%. How much of hydrogen in the sun is involved in the hydrogen burning process? Maybe I also talked about this percentage at some point of time. I didn't remember exactly, but yes, can anybody please try and tell me that what may be the possible answer. Goduli is saying that it is 10%. Option C. Okay, I have forgot to write here the ABCD thing. Consider it as ABCD. Anybody else?
10%.
Okay, Pintu is saying 10%. Anybody else? Okay, let me answer it. It is of course 10%. The answer will be 10%. Those who are not aware, please remember it. Then the question 4, which is at the energy of 1 kilo electron volt, the order of tunneling probability for proton-proton fusion is what? The formula of tunneling probability that I was written in the previous day lecture, and I shown to you today also. Tunneling probability is the thing which maybe we can um, which we can denote with the P, and actually I denoted with the P in the previous class also. So tunneling probability is P. Then what is this? and what information is given to you. The energy is 1 keV, T9 is 0.01. Now, how to calculate? Anybody has calculated or know or have any idea that how to calculate it? Otherwise, I'll start it. All right, let me do it.
Don't know.
Okay, let me do it. Like, what is the P? P is nothing but 2 pi eta, that I have told you in your previous class also. And those are the main formulas that you need to remember and play with those formulas to get to solve these numerical questions. That's why the previous class was very important in terms of numerical problem solving, say, numerical problems. And yes, and yes, you can definitely check anytime the YouTube link or the drive folder where all the materials are there. Yes, so the probability is e to the power minus 2 pi eta. Then for a pp reaction, or maybe let me write that what is 2 pi eta, that I also written in previous class. It is 31.29 z1 z2 mu, that is in AMU unit, and E, that is in keV unit, and the thing which is given to you is also in keV unit. So it will be 31.29 into 1 into 1, because it is PP reaction. Mu is 0.5, that you know, and how 1 cross 1 by 1 plus 1, that is 1 by 2 equal to 0.5. All right, so that is the thing. Then the 0.5 and E is 1. So if you calculate, you will get 2.125. That is the 2 pi eta. Now probability P is equal to e to the power minus 2 pi eta, that is equal to e to the power minus 22.125 and 2.46 into 10 to the power minus 10. That is the order of 10 to the power minus 10. So this is if what is the answer? The answer is option B, 10 to the power minus 10 order. All right.
Ma'am, in the previous, please repeat. Ma'am, T9 equal to 0.01. This data has been used.
No, no, no.
Okay.
It is not necessary. Sometimes there are some extra information is also given there to, like, just to
Yeah.
manipulate you, like you will be puzzled like if I am missing something. But yeah, it's not used here, whatever. So yes, so next question is question 5. Suppose that 4 hypothetical narrow S wave resonances occur at low energies in this reaction. The resonance energies are ER equal to 10 kiloelectron volt, 30 electron volt, 50 kiloelectron volt, 100 kiloelectron volt. The corresponding resonance strains are omega gamma equal to this, and this. Each of these values has been obtained by assuming gamma, capital gamma, whatever, P less than the capital gamma gamma. So, which resonance do you expect to dominate the total reaction rates at T equal to 0.02 gigakelvin? But the thing in this question is that it is written in this huge manner, this question, but there is nothing to solve for it in this question. This can be directly be solved just by using the concept of gamma peak, and you observe that when the gamma peaks and resonance at the and the resonance were plot like these in the lecture, then you observe that the where it came at 30 kiloelectron volt and 50 kiloelectron volt, not other than that. So no, like those are more closer to the other things. So that's why in this question they are showing so many data, like this is this, that is that, but this is just a purely informative question, and you just need to know about the gamma peak and the gamma factor, and what is the resonance energies, and what are the peak that is taking over which energy, that you just need to remember. Then you can solve this question, and the answer of this question is nothing but the 30 kiloelectron volt and 50 kiloelectron volt, which will dominate over the others. Okay, so and at okay, I don't think that I don't need to go through this with some gamma peak and other things again introducing here, because this was already there in the lecture, and I have left with only 30 minutes more, and I need to talk about many more other things. So maybe I can just give you the information that the energy, the total at 30 kiloelectron volt and 50 kiloelectron volt will be dominated over the other. So the answer is B. Now the question 6. Question 6 is consider a resonant state of 1.4 mega electron volt in the reaction to this reaction is given. ECM is 1.2 mega electron volt at T equal to 2.5 giga Kelvin. The measurement results in a resonant state of 1.3 mega electron volt by mistake. Then the factor by which the resulting narrow resonance reaction rate will be high is what? This is a very interesting question, because the presentation of this question is a bit different, such that you will like the student will get like confused that what I need to calculate actually. So let me read this question again and understand that what do we need to calculate. There, it is telling that consider a resonance state of 1.4 mega electron volt in this reaction at ECM, that is equal to 1.2 mega electron volt at P equal to 2.5 gigakelvin. The measurement results in a resonance state of 1.3 mega electron volt by mistake, but it has calculated at some other. So then the factor by which the resulting narrow resonance reaction rate will high. We just need to calculate the reaction rate ratio one with respect to the other. And that is the thing that we need to, why that way we will be able to understand that this is the factor. They have asked about the factor, like then the factor by which the resulting narrow resonance rate will be high. So the factor is that from by calculating the ratio directly we can understand what is by which the which is the, what is the factor by which if we multiply then we will get back the original thing. So we just need to calculate the reaction rate ratio, sorry, reaction rate ratio, and that is equal to reaction rate. We know that it is equal to 2 pi by mu kt whole to the power 3 by 2. If anybody has forgot about this formula, then please again go through this in the lectures. And this is again mu kt by 3 by 2, the same thing obviously. I'm denoting it with the E and it is with the T because the energy temperature is also a term of energy, and the difference, the mistake was there, just the as it is given as t equal to 2.5 gigakelvin, just it is just the notation that E and T I am writing with. Okay, so what are the difference now? Finally if we cut off all these extra terms, then what we will get is this was there, and I have taken it to the denominator to numerator. That's why I am writing it in this manner. Then what was the difference? Difference was 1.4 minus 1.3. that is into 10 to the power 3. Writing the temperature as in terms of energy, because energy is nothing but a form of temperature. So this is the thing, but with this I have kt by, so e to the power 0.1 into 10 to the power 3 by kt means 0.086 into 2.5 into 10 to the power 3 equal to 1.59. So this is the answer, that is option B. The thing is that you need to understand that the factor by which the resulting narrow resonance reaction will be high is nothing but you need to calculate the ratio of rate of the reaction rate at two different temperatures. Which one is greater? Obviously this E with the 1.4, that is greater, that is very obvious, for very obvious reason, and this that is greater by a factor of 1.59 per 1.59. So now you can tell that the factor, or if you, even if they want to calculate something else, you can calculate that what the thing that is need to be calculated here. Now the next thing is, in a stellar plasma, the nucleus 25 aluminum may be destroyed by the capture reaction. The reaction is given to you, or by beta plus decay. That is T half is equal to 7.18 second, and the neglecting other processes determine the dominant destruction process at a stellar temperature T equal to 0.3 gigakelvin, assuming a reaction rate of Na sigma V equal to this, and assume a stellar density of rho like this. So this is the question 7. Now they are asking for which reaction is the more suitable reaction for this, and which reaction is happening on. So for that you need to calculate the mean life. If you can calculate the mean life, and you can see that which has the more mean life, that will be obviously the actual reaction which will stand here to produce this reaction. So you need for this type of question, you just need to calculate of the mean life of this 25 aluminium by beta decay and by the proton capture, because neutron capture and alpha decay, these are not possible condition for this reaction. And how will you understand that? Because in a neutron capture, obviously there have to have some neutron in the reaction. You can see that the reaction is written as 25 ALP gamma 26 Si. Okay, so that means there, which can happen only, that is the either somewhat related to the proton, or somewhat related to the beta decay, because in the decay process, in the beta decay process sometimes gamma produces, but neutron capture, they use the gamma as a, not as a producing component, but rather as a projectile component, and alpha decay is also not possible. So the possible thing is either proton or beta decay. But even if you consider about this case, particularly this reaction, then you can even tell just by seeing this reaction that it will be proton capture, because in beta decay, in here it is talked about beta decay, but can you see here anything about the electron, like electron is coming out or going out or capturing, or somehow the electron related, there is nothing here to related to the electron. So beta decay is also not a possible thing. So proton capture, we can just say it by seeing the reaction itself. But even if you want to calculate, then you can calculate the mean life of proton in the beta decay of aluminum 25 in proton capture and its beta decay, and I am sure that you will get more mean life in case of proton capture rather than the beta decay. So in this question, either you can calculate it or you cannot. You have not, you need not to calculate it. But if you want to calculate it, I am just writing the formula, because you need to remember the formula also in for the other purpose. Maybe this type of question is not there, but somewhere you need to calculate the mean lifetime for the beta decay, and that is nothing but the tau beta plus 25 aluminum, and the formula is T half by ln2. Everything is given to you. T half is 7.18 second and ln2 is 0.693, and it will become 10.36 second. And if it is P capture, then tau P 25 aluminum, that is rho xh mh, that is given to you again, every information, and Na sigma V inverse. So if you calculate this, then it will be like 10 to the power 4 gram per centimeter cube, that is a rho. Xh is equal to 0.7, mh equal to mass of hydrogen in U, that is the 1.0078 U, and Na sigma V, that's inverse, that is the 1.8 into 10 to the power minus 3 inverse. If you calculate, then you will get 0.08 second. So this is the dominant one. So what will be the answer? Answer is A, proton capture. Now the question 8. Question 8 is telling when a 7 lithium nucleus is bombarded with protons, alpha particles emerge. Calculate the kinetic energy of each alpha particle, assuming the kinetic energy of bombarding proton to be negligible. Nothing but you need to calculate the binding energy or the energy difference that is happening during this bombardment or the reaction. What is the energy difference? That is just because of the 2 alpha particle that has been produced, and if you divide it by the 2, then you will get that you will get the energy of 1 alpha particle. So here you need to calculate the kinetic energy of each alpha particle, that is the one alpha particle with which energy, what amount of energy. So the energy released, that is the gap of the energy that has been produced during the bombardment, and that you need to calculate. That is equal to energy released equal to m7 lithium plus mp minus 2 m alpha. Everything is given to you. Why I am writing in this manner? Because 7 lithium nucleus is bombarded with protons and alpha particles emerges. Okay, so what we need to calculate? 7 lithium plus proton minus m alpha, that is just because that is because of the alpha particle. So what is the thing? That is 7.016004 plus 1.007826 minus 4.002603, that is equal to into 931.5 MeV. You need to calculate in MeV order, and I showed you in very first class or second class that how to convert these things. So this is 17.35 mega electron volt, and
2 will be multiplied with that 4.002.
okay, yes, thank you. Absolutely right, there will be 2 into this. So now it will become 17.35. Now 17.35, that is the total energy released between when this reaction has happened, and in this reaction 2 alpha particles has been produced. So what is the energy for each alpha particle? The energy of each alpha particle is nothing but 7.35 by 2, that is the 8.67 mega electron volt. That is option C. Now the question 9. Question 9 is telling that calculate the mean lifetime. mean lifetime that of a deuteron against destruction by the dp gamma 3he reaction, dp gamma 3he reaction for a temperature of T 15 megakelvin, a density of rho 100 gram per centimeter cube, and a hydrogen mass fraction of xh equal to 0.5. Use the following numerical values for the reaction rate. The other variables which you need to know, that is also given to you. So I have just calculated that for the like for a lifetime of a calculating the lifetime for a deuteron against this kind of for this kind of p capturing reaction. This is also a p capturing reaction, right? You need to remember, you need to understand that what is a p capture reaction, because this is capturing a p and producing a gamma and 3he. That is why it is calling it is called a p capture reaction. And this p capture reaction, for these the mean lifetime is nothing but what I have shown you here just before some time, this one. So the formula is mean lifetime tau p of d here, rho xh by mh n a sigma v whole, this inverse. Now if you calculate 100 gram per centimeter cube, that is given to you. I am not writing the units anymore. XH is 0.5 and the 1.0078 U, that you know. I have given written that in the previous question also. Then Na sigma B, that is given as 1.01 into 10 to the power minus 2, that inverse. If you calculate, it will be 1.99 second, that is equal to 2.0 second. The answer is B. That is how you need to calculate the mean lifetime in case of any proton capture reaction. Now the last but not the least, question 10. Detection of 1.8 mega electron volt gamma rays shows presence of which element at astrophysical sites? Okay, detection of 1.8 mega electron volt gamma ray. This is produced for which element? For which element we get this energetic gamma? And the answer is 26 aluminum. That is just an isotope of aluminum. And so the answer will be C. This is another informative question. Okay, so these are the questions that I wanted to discuss with you, and these are the main numerical questions that you may you should be able to go solve it by yourself now. But apart from that, though it is 15 minutes late, but I have a plan to show you the website that I was talking about, and then I will also talk I'll just start the modeling of a star, but not totally. It is not possible to complete it today, but yes, let me first uh, share my screen and show you the website about which I was talking about. The website is called NNDC, which is NNDC website is operated by National Brookhaven National Library, and I hope many one of you who are interested in energy physics or maybe particle physics or nuclear physics, they, or maybe not even those things, but many one of you are already aware about Brookhaven National Library, because they laboratory and library, they provide many things to us for to the scientific community, with and these are being updated on regular manner, and these are the source. Not even, these are not just for showing an website, but these are the source from where scientists also get the regular update and the data to work with any isotopes and isomers or any nuclei that they want to calculate or do something and check something. And these are all verified with the experimental verification also. So let me share the screen of that, and then I'll So I hope now you can see my screen and also can see the website of NNDC. Right? Let me write it in the chat box also. What you need to search in the Google. Just go to Google and search NNDC. I Let me show you NNDC. Everybody please check after completion of this discussion session, or maybe you can check now also. The first option what you will get here is National Nuclear Data Center, NNDC, and go to there. And this is the website where you can see that the first page where which it is what it is showing the stability graph of nuclei. We know that the plot of Z versus N, N versus Z, that is plot over here, and that is called the stability graph of nucleus. And that is not a single line, that we have already talked about in any of the discussion session, that because of the greater number of neutron, sometimes we don't get the exact straight line of when we plot the N versus Z plot, and that is what it is showing here. And the greater number of nuclei is just happened just because it want to stabilize anybody in the universe that wants to stabilize itself. That's why the for the stabilization purpose, the number of neutrons sometimes increases. Sometimes, no, not sometimes, for the heavier elements you can find the number of neutrons is much greater than the number of protons. So if you now go to this page, then you go to the new dat, this thing that is showing over here, that here NSR, new dat, sigma, this new dat. Then if you go to new dat, then you will get some page like this. Now here you can see this is interactive. This is an interactive website, and you can click over any, here it is showing 76 AC. If you click over here, then you will get the information of it. This is a stable nucleus, 9.37% that we get it. And this is the isomeric state information, that is the 34 AC 76, and you can get whole lot of information about this nuclei and atom. uh, all of them are given here, and even you can calculate the ground state here also. This is given at Jn 0 plus. Okay. By just by seeing that, you can understand that this 76 is just a even nucleus, and I told that for even nucleus you will get a 0 plus state. Okay, so the mass excess, that is the binding energy, you can calculate that is also given here for the in terms of kilo electron volt. T half, that is a half lifetime, that is also little stable because it is higher. Then the abundance, like we talked about the abundance of the element, then the abundance is 9.37% in whole lot of other elements. Then you can also check the list of levels, interactive level scheme, J versus E star plot, J versus gamma plot, band parameters, E gamma versus J plot. Everything is given there. Like, let me take any known nuclei, suppose 5. You can also search it over here. Like here I am writing 5 and giving a search, then it will automatically take that 5b10, 5b10, the boron. So it is telling that stable, and the abundance is 19.9%, and the E level is the ground level is 3 plus, E level is 0.0, decay modes, list of levels, and everything is given there. If you want to see the level scheme, then just click over here, and you will get to see the level scheme also. If you want to see the J versus E gamma plot, then you can see the gamma energy versus J, that is the total angular momentum plot. This is the level scheme, that is a non from uh, which state to which state it is jumping and producing what amount of energy, what is the probability that everything can be 1 minute, that everything can be seen over here. Okay. So this is a very nice tool for the nuclear physicist as well as the nuclear astrophysicist to get to know about any nucleus. I want to show you one such nuclei where you can get them where we can get some easier thing. Let us go with the uh, 1h 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 is showing 1h1 Jn plus half plus level scheme. Everything is given there. Interactive level scheme, that is beta. That is, you can actually uh, get anything that you want to know and want to learn, that everything is given over here. This is just a half plus state, which is a very stable state for 1h1. That is, that is why it is showing just one band. But here you can see that when you are seeing the level scheme of something, it was for, I think, boron or whatever, I forgot. For that it is showing, it is showing such many things. Such many things can happen over there with the all whatever it is showing is in on the basis of cell model. That's why I was focusing on cell model so much. So you can just play with it, and if you want to learn, or one more thing I can show you, like level of spin parity, final level plot. If you just play with it, and you can see that it will show you everything, band spacing, level width, everything is given, like whatever you want. And yes, and there are this kind of this black line is actually showing the stable nucleons. And apart from that, what is the deviation is there? The deviation is just because of the greater number of j or neutron, and that is giving the that is making it unstable. And also you can find out that what is the number of it, and what is the abundance of it, and everything. Even this is only the information about the half lifetime. You can also go to the decay mode, and you can get the information of decay. Again, let me go to the lithium, suppose lithium, and in the decay mode, if you get that list of levels and level scheme, then you will get something else again. My I don't know, it is showing error at this moment, maybe because of not good internet. But yes, you can check by yourself. Decay radiation information. See, I just chose a random nuclei, and just click over there, and you are getting that list of levels, interactive level scheme, everything, and decay radiation information. I went to the decay radiation information, and it is giving that what are the decay mode that can be happened. Parent E level energy level is 908 kilo electron volt. Then the parent J, like the ground state is 9 by 2 plus, and everything is given here. Then you can download it as a file also. You can see that it is also talking about that which one is auger effect has happened, which one is the electron capture, what was the beta decay, k alpha decay, beta decay, every information given here. This is in terms of electron, this is in terms of gamma, x-ray radiation, everything. So this is the website that I want to mention, that you just play with it and just check it by yourself, that what other information you want to get, that everything is given over here in this website. Okay, all right. So now just stop my this screen, and I will present my mm, now I want to do the, okay, now I'll present my writing pad, and I will just start the modeling of a star today, and show you the assumptions, that how we start the modeling of a star, and what are the assumptions that we take. And I'll end up today's class now. Then I will leave the other part for the next class. So modeling of a star, what do you mean by modeling of a star? Modeling of a star, why we are talking about this? Because Okay, modeling of a star, because anything you want to address, you want to know that how it works, or do some simulation, or produce some replica of it, or how it is working in terms of some equations, then you first need to model it. Like, what is the ideal and simple condition first, with which I can consider this as a star. Suppose if you want to describe a human, model a human, then what you will say? Some information that we need to have some, like some we don't know about human. That's why we want to model it. Like star is very far away from us. That's why we don't know anything about this, and that's why we want to model it. That how, if with these conditions, this star is working as a star and proper, it is a proper modeling or not. Like, for anything, like for a human, if you don't know about a human, then you have to have consider some assumption that it has about some height, it will have a head, it will have two legs, for two hands and all those stuff. If you consider that, and you will see that it can breathe, it can walk, it can talk, and some of the assumption take, and now you are writing those in terms of some equations, and you are presenting that maybe this is a model. And that is what we do in case of robotics also. Like, we make a model. Robots are also based on some modeling, and everything whatever you want to, like, any plasma modeling, solar star, so sun, the what is going on inside the sun, that is also one kind of modeling. You need to consider some assumption, and you need to go through the equations, that what maybe the equation correspond to these condition. And then we need to find out the variables, which are the proper variables, that is the varying over the time or over the spatial domain. Then we can write few equations and maybe solve it, and we can find out that how over the time and over the spatial domain it will vary, and that's how we can tell about its dynamic. So this is what we will do for the modeling of a star also. So first, let me give a very simple definition of star, that if it is an ideal thing, then what may be a simple, very simple definition of star. That can be like, a star is a gravitationally bound object. Gravitation Gravitationally bound object that emits its own radiation. That is what we have learned in our own radiation. That is what we have learned in our school days, very beginning at class 5, 6 level maybe. That it has some gravitational effect, gravitationally bound some object. Our Earth also, maybe that is not a star. It can a planet cannot emit light, but a star can emit light, and it is a gravitationally bound object. This is the simplest definition that is possible of a star. A star is a gravitationally bound object that emits its own radiation. Now, with respect to these, what are the assumptions that we can do is that there are five assumptions. First assumption is isolation. Most of the stars, like if you consider, they are astronomical unit apart, light years apart, very far apart from each other. So if I consider a star here and another star here, and these are astronomical unit apart or parsec apart, megaparsec apart, then we cannot consider one star's effect on other star. For that reason, we can just simply consider that isolation is possible, and there is no attraction and repulsion on any other effect for other star at this moment, because we are considering an ideal modeling. Okay, this is a very basic modeling, and this runs well for doing a model, for modeling a star. So the first condition is isolation. That means there is no influence of any other things externally. Second thing is composition. Obviously, it is made up of something. That's why it is a 3D object. And what it is made up of, mostly it is hydrogen and helium, we know. And if we don't if we considered a star as a very primordial stage, then we can consider maybe it is about 70% and it is about 30%, and heavier metals are not present. Okay, so this is by mass. Okay, so if we consider this, then we are considering this also, like this is a very basic star, only hydrogen helium, no heavier element. And if it is heavier elements are present there, then it is very small, such that we don't consider it. And this is 70 and 30% by mass, that is totally hydrogen and helium. Now the third thing, that assumption that we take, is spherical symmetry. Spherical symmetry, because at as far as now, or whatever we consider a star for doing a modeling, though it is not a exact sphere, but we consider it as a spherical sphere. That means it has a spherical symmetry and the stars are sphere, absolute sphere. It is not a sphere at all. Maybe I can, yeah, this is a sphere, not a sphere, this is a circle. And if it has some 3D effect, then maybe it is a sphere. Maybe it is not looking a sphere. So let me draw a circle. Okay, so this is this is a star. Suppose this is a star, and which has a spherical symmetry. Composition is only hydrogen and helium, and this is totally isolated, no influence with each other. So this was the third assumption. Now the fourth assumption is the star is in local thermodynamical equilibrium. This is a very important assumption, because if you don't consider this, then nothing will be stable. Anything, if it is a star or anything, it is, if it is an object, then it need to be stable. Without stabilization, it is not possible to exist as an object. So so for existence of it as an object, it must need to be in thermodynamical equilibrium. And that is a fourth condition or fourth assumption of it. And now the fifth assumption is over shorter time scale, L, that means luminosity, temperature, that means T, that means temperature, and R, that means radius of a star, seem to vary. Obviously, it will vary with the time. At t equal to 0, we consider it made up of hydrogen and helium, and it is spherical. It is not increasing, nothing is happening. But we have studied the life cycle of star. But we have seen that with the time span of its life, it starts to increase and become a red giant. That means the mass is changing, radius is changing, and it is becoming hydrogen helium to heavier elements. That means the composition is also changing. So we need to consider the changes. That's how we can do the proper modeling, and we can consider that what will be the dynamics of it, and what will be the equations with which we can deal to model a star. So this was the fifth and last assumption that we take. So according to these five assumptions, we can define three main things which are varying. That is the density, rho, that is a function of mass and temperature. Like R and T, or M means also directly proportional to the radius, that is the R and T. And then temperature, that is also a function of M and T, that is the radius and the time. And Xi, if you consider the composition, then that is also a function of M and T. So main thing which are varying over the time, that is a density, and radius and mass, all those volumetric parameters, those are changing. Temperature, obviously, that is changing, and composition, that is changing. So these are the variables we have. So now we know that what are the assumptions. Assumption or isolation, composition. It is made up of hydrogen, helium. Spherical symmetry is present there. Star is in local thermodynamical equilibrium, and fifth is over shorter time scale. These are not of a star is seen to vary. Okay. So and these are the variables. So now we have the conditions and variables. So once we have the condition and variables, now we can just simply use the conservation of energy, conservation of momentum, and thermodynamical conservation. All those things. Those are the basic fundamental equations which are truth for every case. And by using those things, we can do a proper modeling of a star. And that is what we will do in the next class. And end up the modeling of a star. But this is a very important and crucial part to start the modeling of a star and understand that what are the assumptions that need to take to model a star and what are the variables. So now after that we'll do this. We'll just solve the equation. Maybe there are a lot of equations that need to solve to get reach to the destination. Maybe 3 and 4 pages of my handwriting, 4 5 pages. So I will not do it today. I will end up today with this message that what is the modeling of a star, and for that what we need to do, consider what are the assumptions and what are the variables. And now we are totally set to solve the equation, to write the equation and solve it and get the equations that how we model a star. So I'll end up here with the things that let me revisit again. I'll not tell it again and again, but I will tell that what we have covered today. We have done the revision. Then we have solved some question, talked about the few important and interesting topics, and interaction matter. What are the basic fundamental particles? Then again we solved some new problems and questions. And I talked about the NNDC website. Maybe let me write it here such that you can remember it on when you see it later. NNDC website that I talked about, you can check it and play with it by yourself. When I was taking a nuclear physics course, then there used to have some questions directly from the NNDC website. We need to use that website and find out that what is the tau or something, the level scheme of that, and then we need to calculate and draw and produce the patterns and produce something. So that time I learned that how this website is important, and no one actually can make you understand that how it works and what are the features of it. You need to play with it yourself, then you can understand.
Excuse
And
me,
last
ma'am.
but not the least, a modeling of a star. That's I have just started, and the assumptions I have told and the variables I have told. I'll next day go through all the equations and the what is the solution that we'll get to model a star. Those things will be discussed, and the further new topics will be discussed in the next week. So I hope it
Ma'am,
is yes.
ma'am, I have a doubt, ma'am.
Hmm.
In nuclear reaction processes,
Mhm.
which one require more energy, ma'am? Either nuclear fission process or nuclear fusion process, ma'am.
That by now I think you should have understand, and you tell me which should be the which should need the more energy, more temperature.
Maybe nuclear
If two
fission.
hydrogen is making a helium, that needs a more energy, or if a helium is producing two hydrogen, that needs more energy. Calculate it and tell me next day.
Okay, my guess is nuclear fission process, I guess, ma'am, but I don't know exactly.
Maybe you can this is a very bad idea, but you can search in Google also, and you will
Okay,
get
okay,
many materials there also. But I will suggest don't do that, and
okay.
try to take some example by your own, and you now know what is the amount, how to calculate binding energy and how to calculate the energy released and extra energy that is required for the reaction. You calculate it also by your own, and you will easily get the answer which need the most more energy, more temperature.
Okay, ma'am. Okay, ma'am. Thank you,
I'll
ma'am.
surely ask you and talk about this in your to you with the next class.
Okay, ma'am. I'll try, ma'am.
Okay, sure. Okay, I hope every one of you are enjoying this course. And yes, anything, anytime, you can ask it write in ask a question portal. You can visit the YouTube. That's I usually used to tell every time. And now let's wrap up this session. Okay, bye.
Thank you, ma'am.
Okay,
All
ma'am.
right. Okay,
Ma'am,
Nanda Kumar is talking about the notes. Notes are given in the drive folder that you can share your. You can ask for an access to me and send a mail. Then I will give you the access for all the materials that I am using, and I have uploaded all those in a folder. But you need the permission for that. You just need to send me an access request.
okay, ma'am. Thank you, ma'am.